Okay, this is day 4 of Unit 5. We started by just discussing the lab from last week. So the answers that we came up with to the questions. So these are on the top of page 9. How can we tell where the zeros are located on the graph if you're looking at the factor polynomial equation? So you should have looked back through the different equations. Like if I'm looking at number 1, I see x minus 2. All right. I don't know what's going on here. Let's try a different pen. So I'm looking at x minus 2 and x plus 5, the quantity squared. So if I'm looking at that equation, how can I tell that the roots are at 2 and at negative 5? Well, I set y equal to 0 and I solve using the zero product property. So basically, when we're looking at the equation, we can just see that the 0 is going to be at the opposite sign of whatever's in the parentheses with it. So x minus 2, that means 2. So second equation, or second question, what happens to the graph at the zeros when the corresponding factor in the polynomial is linear raised to the first? So again, if I look back to the first equation, we have y equals in front of that. The x minus 2 is raised to the first, so that's what it's referring to. And if you look at your description for that one, we said that the graph went through at 2, 0. Now, you can't make a generalization based on just one fact. So if you look at the second equation, we have x minus 2 to the first, x plus 2 to the first, and x minus 3 to the first. All three of those are to the first, and all three of those went through the x-axis at those zeros. So we can generalize now when we have something, a factor raised to the first power, it's going to go through the x-axis at the root. Okay. On the other hand, if we have a squared, like we do in equation 1, we have x plus 5 squared, there it bounced at negative 5. And same thing, any of the ones that have a squared, like equation number 4 has a x plus 3, the quantity squared, and it also bounced at negative 3. So it's going to, if it's cubed, or I'm sorry, squared, it's going to bounce at the root rather than going through the x-axis. So if the factor is cubed, then what's going to happen? Well, there's only one equation that had a cubic factor, and that was number 5. And what happened there, I'll just quickly sketch that graph. So we had 0, 0 was a single, and then negative 4. What happened was it came into that point and then went out of that point with an opposite concavity, and then it went through. So because, and it's kind of hard to tell here, because it's coming in one direction and going out the opposite direction, that point right there is a point of inflection. And we talked about that last week. So if I look at just this piece of the polynomial, not the whole polynomial, but just that piece, it looks like it's cubic. So, and it looks like it's cubic because there's that point of inflection. So what happens? You'll have a point of inflection at the root. Okay, so moving right along to the next set of questions. Next, they're dealing with the degree. Well, if you look through all the equations that have an odd degree, which would be numbers 1 and 2, those are degree 3, they have end behavior of down, up. Now, there's none in the lab, but another option for odd degree is it could be up, down end behavior as well. The easy way to remember that is odd starts with an O, so O for opposite. The ends will be opposite from one another. On the other hand, if it's even, even makes you think equal, meaning the ends will go the same direction. So either down, down, or up, up. And hopefully you saw that in the lab. There were several that were degree 4. Some of them had down, down, and some of them had up, up end behavior. So then what's the most number of zeros a degree 3 polynomial has? Well, if we looked at the degree 3s, that's questions 1 and 2. Question 1 had 2 roots, and question 2 had 3 roots, and they were both degree 3. So the most it can have is 3. On the other hand, the ones that were degree 4, which would be 3, 4, 5, and 6, were all degree 4. 3 had 4 roots, 4 had 3 roots, 5 had 2 roots, and 6 had 3 roots. So the most that I said there for all those degree 4s is 4. So it can have 4 or less roots if it's degree 4. So generalize here, if it's an nth degree polynomial, it can have n or less roots, not more though, only less. Okay, and then we got to talking about, well, why does that happen? So why would we have less? So for the third degree polynomials, why did one of them have 3 roots but the other one only had 2? So we looked at that and we realized that number 1 had 2 roots but it was degree 3, and that was because of that double root. Whereas number 2 was degree 3 and it had all of the factors were just to the first power, so no squares. Same thing with the degree 4s. Number 3 was degree 4 and it had 4 roots, so it went through 4 times the x-axis. But number 4 was also degree 4, but there were only 3 roots, and that was because one of those roots was what we call a double root. It's because of the x plus 3 squared. So because of that squared, then there's 1 root less than what the degree is. Okay, and cubic roots are also going to cause you to have less. So like number 5 is degree 4, but one of those roots is a cubed root, or x plus 4 is cubed. So that accounts for 3 of the 4 of the total of 4. The degree is 4. 3 of those roots, let's say, is the x plus 4 cubed. So that's a triple root, we call that, which means there's only 1 single root. So total, there's 2 different roots in number 5. There's a root of x equals 0, and there's a triple root at x equals -4. So there's 2 total roots for that, even though it's degree 4. So what causes us to have less roots than the degree would be double or triple roots. Okay, so the next thing we looked at was the characteristics on page 9. So basically, I just kind of said that a moment ago. So if I have a single root, an example of that would be something like x minus 5. Well, that's to the first power. So that means that's a single root, which means it's going to go through at 5, 0. On the other hand, if I change that to a double root, that means the x minus 5 quantity is going to be squared. And so it's not going to go through. We know it's going to bounce at 5, 0 because there's a double root there. And lastly, the triple root would be the same equation, but this time the quantity is cubed, which means that it looks cubic at 5, 0, or in other words, there's a point of inflection at 5, 0. Okay, so that takes care of the root behavior. Now let's talk about the end behavior. So this really is just summarizing what we've already said. We said that odd, opposite, so either up, down, or down, up. Now remember from our previous unit that on the right-hand side, if it's pointing down, that means the graph has a negative orientation. So negative points down and odd is opposite, which means negative and odd is going to be up, down, which leaves down, up for positive and odd, pointing up on the right. So even we know has to point up on the right for positive. So that means up, up, because even they're the same, equal. And for negative has to point down on the right, which means down on the left as well. So those are your different end behavior options. Okay, the next thing we looked at would be page 10. So page 10 starts by asking a couple questions that we've already covered. So it says, what is the maximum number of roots a polynomial of degree 3 can have? That we know is 3. Then it says degree n can have, we know that's n. Then can a polynomial of degree n have fewer than n roots? We said yes. And then it says under what conditions? Remember, if there are double or triple roots, then an nth degree polynomial has less than n roots. Okay. If all the roots are single roots, then n will equal the number of roots. Okay. So D, for each of the functions, state the minimum degree its polynomial equation could have. So I explained a real quick, easy way to do that. You count the directions. So if I'm looking at A's graph, this is one direction, and then it hits this point and changes direction, so that makes 2, and then it changes again, that's 3. The minimum degree this polynomial can have is 3. B, same idea, 1, 2. 2 is the minimum degree. C, 1, 2, 3, 4, that's 4. And D, 1, 2, 3, 4, 5. 5 is the minimum degree. So then part E, which of the graphs above have a negative orientation? How do you determine the orientation? Well, we just said that a moment ago. The two that are pointing down on the right are B and D. So they have a negative orientation because negative orientation graphs point down on the right. So next, you're supposed to take a look at the graphs of y equals x squared and x to the 4th. If you do that, if you take time to type those in your calculator, well, first of all, we already know what x squared looks like. But if I take a moment and graph x to the 4th as well, I'm going to see that it looks pretty much the same. It's slightly flatter by the vertex, but it's really, really hard to tell that and really hard to tell them apart. So without knowing that this is y equals x to the 4th, I may confuse it with y equals x squared. So having said that, could graph B have degree 4? This is question 2A. Could it have degree 4? Yes, it could, because it looks like a parabola. I don't know if that is degree 2 or if that's degree 4 or 6 or 8. I don't know that by looking. But I do know that the minimum degree would be 2. It could be higher than that. It's not going to be smaller than that, but it could be 2, but yes, it also could be 4. So yes, it could. Part B, could it have degree 5? Explain. We just talked about that in class. It cannot have degree 5 because 5 is an odd degree. Odds have opposite ends, and graph B is pointing down on both sides. So it has to be an even degree only. 2, 4, 6, 8, so forth. Can't be odd. Can't be 5. So that's a no. Okay, so that was it for in the packet in terms of notes. I did give some more notes that students put in their notebook. So we did this one together in class. So reminded you what the number line looks like. So the number line, what that means in terms of the lab when we did it was the open points represented, if you recall, the roots. So I'm going to put a root at 0, at +2, and at -2. And then if you recall, the shading occurred where the outputs were positive, or in other words, where the graph was above the x-axis. So if I have to make a graph to match this number line, think about how that would look. Well, it would have to be above from -2 on to -infinity. And then it has to cross because I see here it's not shaded, which means the outputs are negative. And then it has to go back up and touch 0, 0 because there's a root there. But notice I shouldn't keep going because it's not shaded after 0, which means it bounces there, goes back down. Then I am going to go all the way through because I see from +2 on it's shaded. So your sketch should look something like that. Next, this will also go in your notebook. So we started with this equation. So if I start that equation, I'm going to actually list the degree first. And the degree I can see is 3. The end behavior, well, I know it's odd. Odd are opposite ends. So either up, down, or down, up. I'm also looking at the equation and seeing this negative in the front, which I know means it should have a negative orientation. So opposite and negative orientation means up, down has to be the end behavior. Next, the roots. So I'm going to write those as x equals, and not only am I going to list the roots, but I'm going to try and go in order from left to right because I'm going to be graphing these in a minute. So I can see the smallest root would be -3, so I'll list that one first, and then 0, and then +5. So I'm also going to take a moment and decide if those are single roots, double roots, triple roots, or a combination of. So they're all to the first power, which means they're all single roots. So when I graph those, I'm going to make sure that I go through at each one of those roots. So now I'm going to go ahead and make myself a graph. So I'm going to plot a point at 5, 0, another point at 0, 0, and lastly a point at -3, 0. I'm going to put the ends on. I'm going to make the left end pointing up and the right end pointing down. And I already said that it's going to go through, so I'm just going to make it go through at each one of those values and label -3, 0, 0, 0, and 5, 0. Okay, and that's my graph. Now, I did discuss in class, you don't know yet how big to make these loops that connect the one root to the next. You don't know if you make it real small or if you should make it real big. You don't know that yet. And same thing up here, this loop. So I'm not expecting you to know that, which is why we're calling this a sketch. Later, when you get to calculus, you'll learn more about those loops and how big to make them. And so at that point, you'll have to make them accurately, and it'll be called a graph. For now, we're just doing a sketch based on the information that we currently have. So next one, copy that equation into your notebook. We'll start with the degree. So I can see degree is 4. 4's equal or even, so equal. So either up, up, or down, down. I don't see a negative in the front, which tells me positive orientation, which tells me up, up. The roots, I'm going to go in order from left to right. I can see x equals -3 would be the smallest, -2 would be next smallest, and +1 would be the biggest. And -3 and -2, those are singles, but +1 is a double. So I'm going to remember to make that bounce. So at -3, I'm putting a point. At -2, I'm putting a point. At +1, I'm putting a point. My ends, up and up, so pointing up, I'm pointing up on both sides. So it's going through at -3, it's going through at -2, and it is hitting and bouncing at +1. So my graph looks like that. Okay. And the last example for today. So I can see degree is 5. And behavior. So I know up, down, or down, up. I see no negative sign in the front. So down, up. Roots. Looks like -2 is my smallest, then 0, and then 4 coming from those factors. -2 and 4 are singles. and 0 is a triple. So let me plot those. So at -2, putting a point, 0, putting a point, +4, putting a point. End behavior. This is coming from down, and this is going up. And so I'm going to go through at -2. So when I do that, now I know this next one is a triple. So I'm going to, it's coming from above and it's coming from to the left. So I know it's curling in there. And now I'm seeing the concavities concave down. So this is a triple root. So I need it to be a point of inflection. So I'm going to make it curve out in the opposite direction. So it's concave down, now it's concave up. And then I'm just making it go through there. So I have clearly here a point of inflection rather than just going straight through from the one point to the other. So that's a point of inflection at 0, 0. And then I have a through at 4, 0. And a through at -2, 0. And that is my sketch. So tonight for homework, you are going to work on page 10 and 11. You're going to finish those up. We did some of those pages, but you're going to finish. And then in worksheet 3, remember we're in unit 5 now, you're going to do problems 9, 10, 12, 13, and 14. You do have a quiz coming up on Wednesday. And don't forget to bring money in for the angel tree if you can. And of course, we have to look at our meme. So forgetting to feed your parrot is polynomial, polynomial, polynomial. Okay, so do those problems for tomorrow. Have a good night.